So brief recap we're going to have for presentations, and the first one is online, and please keep in mind that it's 5 minutes each. And you can start sharing your screen and beginning. You can go ahead.
Okay, great. Okay, so hello everyone. I'm Jiangkang from Nanyang Technological University, Singapore. Today I would like to share our CVPR work, EgoLife. So to have one sentence to summarize the work, we are inspired by some reality show and have 6 people. They don't know each other before and living together in the same house for 7 days. Each one wears meta area glasses almost all day long, around 8 hours, to get the extremely long egocentric video dataset. To collect the dataset, we set up 15 fixed cameras in the house, 8 on the first floor, 7 on the second floor. They are synchronized with 6 egocentric videos from volunteers. We also have other signals such as MM wave. To further explore the EgoLife house, you can visit our website. It's a very cool house where 6 volunteers are living. Okay. To make sure they have a concrete life goal during the week, we ask them to collaborate to organize the Earth Day party at day 6, so that they should have a diverse but coherent activities. They have meeting, shopping in the day 1, have some singing and dancing rehearsal in day 2, practice some cooking in day 3, and so on. People gradually get familiar with each other, and so that the interpersonal dynamics should be traced. With the extremely long life-oriented egocentric video, we designed 5 kinds of the life-oriented QAs. Most of the QAs require a model or human to trace back more than 2 hours to get the correct answer. 5 kinds of the QAs including record the second song I listened today, where is the scissors, taskmaster is when I walk past a store, I remember I need to buy something, but I forgot what to buy. Some model should remind me I should buy a milk because I found it is out of storage in the fridge in the morning. Habit insight is to find my hidden habit based on my behavior pattern in the past few days. And relation map is to ask interpersonal dynamics. Here is a video to show the QA and how a model should solve the problem. So the question is, how much should we spend on the egg? And the model, we hope the model should trace back, move way back to the shopping mall and find the place where the egg, the price tag of the egg, and do some calculations. Here is the proposed baseline solution for the QAs. We have 2 sections. One is EgoGPT. The EgoGPT basically do the captioning, video captioning. Actually, the omni-modal captioning, because the input is not only video but also audio, so that the caption is incorporate, like the caption incorporates both video and audio information every 30 seconds. So it's there are many captions. We collect them as a memory. When the question comes, we can get all the memories before the question, because in the setting we do not allow the model to get the video after the pinpoint. So there is a keyword extraction model. It's a module, not a model, to extract the keywords from the question and do some query to get the timestamp in the memory and get the evidence, 3 evidence the evidence we can trace back to the video and audio and the captions to input to the vision language model again to answer the question. So basically, the baseline is like this. So we're gonna skip this, and I think that's pretty much of the talk because of the time limitation. So if you want to explore more about this project, please visit this website. Thanks.
Okay, thank you so much. As I was saying before, there's no time for Q&A, but feel free to send an email to the author. And the rest of the presentations, sorry, I was muted again. But thank you for your presentation. As I was saying, there will be no Q&A because of time limitations, but people are encouraged to send you an email if they have questions.
Of course.
Thank you so much.
For not attending CVPR this year, so.
Yeah, no, thank you for presenting anyway. Yeah, all right. And the rest of the presentations will run through this. I have to share, so it should be this one. Okay, hopefully it's working. All right, so the next talk is, I'm not sure how you read it, HAWOR, right? Is it?
Yeah.
Okay, HaWoR. Okay, makes sense. So please go ahead.
Hello everyone, today I will present our work world space hand motion reconstruction from egocentric videos. Let's start by looking at the current challenges in 3D hand pose estimation and reconstruction. Most existing methods reconstruct hand poses in camera space. However, they ignore the motion in the camera itself, so the world camera motion is not captured. You can see this means we can't analyze how the hands move in the real world. Also, these methods treat videos as a set of static frames. As a result, they can't model the temporal dynamic of hand motion. Furthermore, SLAM methods, which are often used to estimate the camera motion, struggle in egocentric settings. You can see they often fail in dynamic environments, and they can't capture the real-world scale. So to address these challenges, we present HaWoR, a framework to reconstruct the hand motion in world space. Let's take a step back and think about what world motion is. We can break it down into three components. The first is the camera space hand motion, and the second is camera motion, and the third is world coordinate. So, let's start by detection and 3D hand pose estimation in camera space. We collect a large-scale data set for hand detection and reconstruction, and we train a model for robust hand detection, and train a large model for image-aligned hand reconstruction. Also, we achieve state-of-the-art detection and reconstruction performance in the wild. You can check our paper or Wheeler in the poster session. Now let's take a look at how HaWoR achieves the world space hand motion reconstruction. First, we observe that hands take up a large portion of egocentric image. So this. Okay.
Yeah, maybe.
Okay. To address these challenges, we propose the adaptive egocentric SLAM, which is specifically designed for this. Specifically designed for this setting, and to fix the scale problem, we introduced a metric prior like metric 3D, which brings everything we need for real-world scale. Finally, to deal with the occlusions and the missing hands in between, we introduce a novel module to complete the task called motion in between. Let's look at our results. As you can see, we achieve accurate world coordinates, camera motion, and better global motion compared to the different baselines. Okay, let's look at the comparison of hand reconstruction. From left to right is the baselines and our method and the ground truth. As you can see, our method has much better results compared to the baselines and much closer to the ground truth. Here's the video. Okay, you can see our results is very smooth, accurate, and reconstruct the world motion of hand. We have different senses, examples. Our results are very good.
To go back to the presentation.
So that's all. Thank you.
Okay, that's all.
Welcome to our poster session. Thank you, sir. Thank you.
Thank you. So, is the speaker for the next talk in the room? VidBot? Okay, come up. So VidBot learning generalizable 3D actions from in the wild to the human videos for zero-shot robotic manipulation. 5 minutes.
Okay, so hello everyone, I'm Hanzi Chen. It's my pleasure to present our work VidBot learning generalizable 3D actions from in the wild to the human videos for zero-shot robotic manipulation. This is joint work by me, Boyang Sun, Aaron Zhang, Mark Polifus, and Stefan Lortenegger. So in this work, we present VidBot, a framework to learn language conditions 3D affordance directly from in the wild human videos. We can see that our affordance model can be deployed across robots and environments to execute all these everyday manipulation tasks. So the first part of our framework is to extract actionable information from in the wild human videos. So to achieve this goal, we have several modules. This COMAP system is to acquire camera poses and intrinsics. And we also leverage monocular metric depth predictor to get the dense depths with metric scale. And also we leverage hand object detector and several segmentation models to acquire the static regions for each frame. So our first objective is to correct the camera poses to the matrix space. So we do this by optimizing a global scale and project these sparse landmarks onto the image plane using the extrinsics and the intrinsics. So we can see that it's converges very fast as it's a scatter. And then our second goal is to refine each frame's poses and the scales to compensate the SFM reconstruction error due to hand object motions, and also make the depths across frames more consistent. So yeah, we formulate this loss term, and we can see that the point distance is gradually minimized after several iterations, yielding more geometrically consistent reconstructions. So we apply our pipeline to this data sets epic kitchens, and we can see that all these hand trajectories. Yep. Then let's come to our second part. Now we have all this affordance data, and how can we learn affordance from such amount of data? So we basically propose a coarse-to-fine affordance model. So the input to our model is a RGBD frame, an instruction, and a crop of the object of interest acquired by a off-the-shelf open vocabulary detector. So we first have a coarse affordance predictor to infer a set of goal points and contact points. So yeah, here are the results. Then, conditioned on this core stage output together with the task observations, we employ a denoising network. It iteratively removes the noise of the sampled trajectory in each diffusion step, and it gives us the final interaction trajectory. And due to the inner wild nature of our affordance data, it's not perfect, and our affordance model is expected to mitigate such noise and also generalize towards new embodiments or new environments. We hence define several test time guidance analytical cost functions. It will perturb the output of diffusion during the diffusion process so as to satisfy this test time constraint. So, for example, this multi-goal guidance here is used to improve the robustness compared to single-goal conditioning, and this collision avoidance guidance here is used to account for the morphology of the robot hand models and also the geometry of previously unseen objects, so as to synthesize safer or collision-free hand trajectories. And here are the final input results, and each color means the cost. Yeah. So our model can actually also be applied to different objects with different instruction to infer the interaction plan, like the open the microwave, take the kettle, or wipe the counter, or take the tissue. Yeah. So to validate the effectiveness of our framework, we also benchmark against several baselines. And we can see that our baselines achieve the best performance with a success rate of 88.2% and surpass the run-up method by nearly 20%. So we also deploy our model to these robots from our lab and have it to execute several manipulation tasks, like open the microwave, open the cabinet, and we can see that it's generalized quite well in these unseen environments. Yeah. And we also want to see that if our model can also generalize to these new robots, so we also deploy it to the spots and have it to execute similar tasks but in completely different environments. And again, we can see it has very good manipulation performance. Yeah. So that's all from my side. And if you want to know more details, please visit our website. And also, I will present our work on Sunday. You are free to reach out. Thank you.
Thank you. All right, so last talk for the session. See, please come on. The paper is Discovering Hidden Visual Concepts Beyond Linguistic Input in Infant Learning. Oh, the green one. Okay, yeah. How do you move it? Oh, okay. I don't know if this is gonna work. Not sure there is any way where it's not going to. At the top. It will like. Which side? This one or this one? Yeah. I think this is the best we can get. Yeah.
Sorry. Sure. It's just easier.
Oh, I see.
And there's a hide, it's a different language that can help.
There is a hide thing. It says hide somewhere? Doesn't say hide in
yeah. Oh, yeah. I see. Why that's not default. Okay, you can go ahead.
Where's my slides?
Next one.
Okay, great. Yeah. All right, so I'm Satoshi from NTU. So today I'm going to talk about something very different from a typical CVPR work. We don't have any new method. We don't have any new data set. Instead, we do science. And we are trying to computationally model how inference learns the names of objects. And hopefully, we can inspire something on computer vision. So how does it have something to do with egocentric vision? So actually, we can use egocentric videos of infants when they are playing with their parents, which I think is a moment that human infants are training themselves to learn the names of objects. So for example, kids can play, with the toys, and then the the parents might say like, hey, look at the door, and do you want to play with it or something like that. And then that's the moment that kids are training their visual representations as well as the corresponding names, right? And then actually we are not the one who collected the data. There's a group of other people who did this, and we are building on top of it. And also, once we have the kind of the actual training data that kids use to train their vision language model, we can train computational vision language model, for example, CRIP, which I think is the simplest vision language model. And so let's just train a CRIP-like model on infant egocentric video frames and the corresponding words transcribed from parent speech. And once the model is trained, we can test the capabilities of the model and see if their performance is aligned with human infants or some developmental theories of the human infants. And again, this is not what we did actually. Someone else did it and published on Science, and then they open source the present model, so we are building on top of it. So what did we actually do? So we analyzed their model and tried to find the evidence that the model trained on infant inputs behaves more like actual infants beyond what was reported on the original study. So to find that, we turned to the developmental psychology and how human infants conduct their word learning or the mapping from the visual concept to the words. So infant learning happens in sequence. First, they learn some visual vocabulary, and then later they learn the mapping to from the vision encoder to the words. And putting this back to the computational side, model should develop visual concept inside the vision encoder, and then later they find the mapping to the text vocabulary should occur if the same process as human infant learning is also happening in the computational side. And I think it does, and it actually does, and we have evidence for it. So that's what our paper is about. So we analyzed the internal representation in the vision encoder, specifically individual neurons inside the encoder, and then discovered that many of them respond to some visual concepts, even if these concepts are never ever mentioned in the parent speech. So in other words, the model had learned to see certain objects, but they just haven't learned yet, don't know the names. So this kind of mirrors what happens in real infants. They often understand visual concept, but they just don't know the name yet. So moreover, we found these hidden visual concepts tend to be higher level vocabulary than those in the text encoder because they just haven't learned the name, but they will learn the name later, right? So it should be the more higher level that is already learned. So to sum up, a CRIP-like model trained on infant egocentric experience knows the visual concepts beyond those provided by parental linguistic input. And the discovered concepts include higher level concepts than those in the text encoder of the vocabulary. And we also have more analysis. For example, the infant visual representation is how do they differ from the CRIP trained on internet data, or how does it differ from ImageNet representation. But due to the time constraint, I don't go through it, but fortunately, this one is also accepted to the main conference. Tomorrow morning, I'm gonna be in front of the poster 401, so yeah, please come to my poster, and then yeah, hopefully we can see everybody there. Thank you.